Hello, my name is Tiago Davi Curi Busarello. I'm a professor at the Federal University of Santa Catarina, Brazil, and the title of my paper is Control Strategy Based on Frequency Response for a Single-Phase Full-Bridge Series Active Filter. Let's start with a short introduction. The series active filters are a mature technology and well covered in the literature, and series active filter is an important technology for power quality improvements in distribution system. The main goal of a series active filter is to improve the voltage waveform downstream of the point of its connection. By employing a series transformer in a distribution system, and controlling the voltage over this transformer, we may shape the voltage to a desired profile. And different power topologies and control strategies have been proposed since the 80s. Nevertheless, the high penetration of renewable sources into the electrical system brought series active filter to discussion again. And the inclusion of PV systems combined with a high amount of nonlinear loads magnified the distortions at the distribution voltage. In summary, the high penetration of PV and nonlinear loads brought the attention of series active filter again. And industries and academias are looking for more sophisticated controllers with superior performance over the existing ones. The proposal, this system shows our proposal. This system is single phase. There is a distribution system here represented by a voltage source and the grid impedance. There are loads, a linear load and a nonlinear load, and the series active filter is made by this H-bridge inverter, the output LC filter, and also made by this transformer. There is a DC bus which supplies energy to this series active filter. And our proposals are based on this list. The paper presents a control strategy based on frequency response for a single-phase full-bridge series active filter, and the series active filter is controlled in voltage mode through a digital lead lag controller. This is the main contribution of this paper. The target is to design this voltage control in a digital environmental, and this controller is based on a lead lag feature. The controller parameters are obtained by frequency response technique using the key factor methodology and later discretized via backward Euler approximation. The delay is taken into account in modeling the system. And in order to show the attractiveness of the proposed control strategy, the series active filter was tested under several adverse conditions like sag, swell, and harmonics distortions at the grid voltage, nonlinear loads, and also on low frequency oscillation at the DC bus. In summary, our proposal is to design this controller, and if we took a careful look at this control strategy, we can see that this is quite simple. We are measuring the voltage at the input of this transformer, I mean the voltage at the distribution system. We are also measuring the voltage at the point of where the loads are connected. Then this first voltage is passed through a PLL in order to result in a clean sinusoidal reference. With this, we can operate this series active filter under distorted voltage. So we compare the reference with the load voltage, and then the error signal passes through this designed controller, which later acts in the PWM and then switches the transistor of the H-bridge converter. Still talking about the proposal, the final target again is to design this controller. This controller is lead and lag and it is digital. So this is the transfer function of the controller. The point is to get the coefficients of this z-domain transfer function. To start getting these coefficients, we need to model the system. And in order to model the system, we can first of all check if the transformer has a big influence on the behavior of the series active filter. And we can conclude that we can neglect the effects of the transformer in modeling the system because the main frequency in which the series active filter will work is 60 Hz. These bold diagrams show that this will have the curves only for the capacitor, and also the resulted equivalence of the parallel connection of the transformer and the capacitance. For different values, we can conclude that for 60 Hz, all curves are coincident, which means all curves are coincident with only the capacitor. So we can say that we can model the system without considering the primary side of this transformer. Because if you look here, we see that they are connected in parallel, but the effect of this can be neglected in modeling the system. Designing the digital controller, we start the designing the controller by defining the desired cutoff frequency and also the desired phase margin. These are the values that we are having to in our closed loop control system, which is 2 kHz for cutoff frequency and 55 degrees for phase margin. Then we can compute a collection of equations in which the final result will be the coefficients of the digital controller. I won't get into details of these equations. I invite you to take a look at the PDF of this paper for more details of these equations. But the point is that we need to compute all of them in order to get the controller. Case study. By defining the system parameters, and they are shown in this table, we can compute the coefficients using those equations shown in the previous slide. This is the final controller. All coefficients are listed in this table. Case study. So, still in the case study, the first thing that we should do is to compare the digital controller with its analog version, because the process of designing this controller starts with design an analog controller and later discretize. So it is interesting to compare the frequency response of the analog and the digital controllers and see how much they are coincident. And this shows that this curve here is for the analog controller and the blue one is for the digital. We are interested in up to 2 kHz. We can see here a great coincidence with a little bit in the phase, displacement in the phase, but this is not so problematic. But we can see that for 60 Hz, we are having a good coincidence of these frequency responses. We can also plot the closed loop, the open loop transfer function considering the controller, and just to check if the desired values were obtained. In this case, it were obtained. We see that the phase margin achieved is 55 degrees, while the cutoff frequency is actually 2 kHz, exactly those that we defined previously as desired parameters. Still in the case study, let's plot the closed loop Bode diagram. This is the result. We can see that the frequency response for the closed loop has a flat behavior up to the response, up to the cutoff frequency, which means that the series active filter will be able to make the output voltage to follow its reference signal without steady state error up to the 2 kHz. In case we need to produce a component with, for instance, 60 Hz, 600 Hz, we can see that the series active filter will be able to do that. Results. The system was tested in a hardware-in-the-loop setup. This is a real-time simulator. This is an interface board, and this is a microcontroller, which is the classic one F28335. The power structure of this system runs within the real-time simulator, while the control strategy runs within the physical microcontroller. We have here a scope just to collect some results available at the analog outputs of the real-time simulators. Let's check some results. The first one is a steady state test, classical. So we have here in orange the distribution system voltage. We can see that it is distorted. In case we do not have the series active filter, any load would receive such an orange waveform, a distorted waveform. But with the series active filter working with the designed controller, we can see that the load voltage receives a sinusoidal waveform. Here in purple is the load current. You can see that in this case is a series, as a combination of a linear and nonlinear load. And in green is the output voltage of the series active filter. The orange plus the green results in the blue waveform. The second case is two tests. This is for non-load and also when harmonic suddenly appears at a distribution system voltage. Initially, we do not have such a distribution, such a distortion, which means that the series active filter is producing nothing at its output, and suddenly at this point we have distorted voltage at the distribution system, but the voltage that the loads receive is still sinusoidal thanks to the series active filter. Another result is when we have a sag from 220 volts to 190 volts. Initially, there is no sag, so the distribution system voltage is already sinusoidal. The series active filter does nothing. At this point, the voltage at the distribution system suffers the sag, but we can see that the load still keep receiving the amplitude that is desired for such a system. Another result is this one, in which we are changing the grid impedance parameters, because usually the controller is designed for a specific case, but we can see that it may work with different scenarios. This is a result showing that. We can see that the blue waveform is still sinusoidal, is a little bit distorted, but is still acceptable to be supplied for loads. The load is still nonlinear, and then we can see that the series active power filter supplies such a waveform in order to make the load voltage sinusoidal. All the results may be found in the PDF. I invite you to check that. There are other scenarios evaluated with these series active filters, like a swell in the input voltage and also oscillation at the DC bus. Here is a picture of the system, the hardware in the loop, the microcontroller, and the scope collecting results from this system. Some conclusions. This paper proposed an accurate, fast, and reliable voltage controller for a single-phase series active filter. Results showed a satisfactory behavior for the series active filters to operate under harmonic distortion, disturbances, and in the presence of nonlinear loads. The system was tested under different grid impedance and presented a similar behavior. Therefore, the control strategy proposed in this paper is an attractive tool for single-phase series active filter. Moreover, the proposal can be easily extended to a three-phase system with control strategy running in a stationary reference frame. For those who are interested, the script and the simulation files used in this research are freely available on my webpage. You can go there and download all the scripts in designing this controller and also all the files used in this research to simulate this system, to test in the hardware loop setup. All of them are freely available on my webpage. Thank you so much. If you have some questions, I'll be so glad to answer. You can type your question and send it to my email, which is written right here. Thank you very much.